Okay, so maybe we want to start, to be roughly in schedule. So then let me introduce Gretchen Matthews. She is a full professor in Virginia Tech since 2018. Before that, she was for many years at Clemson University, where she also was the PI on a huge grant for graduate education, I think it is, was this grant called, it's GR, I forgot the name, the acronym. And now in Virginia Tech, Gretchen is also the director of a center for cyber security. And she will tell us, she is really, I would say, one of these, the experts in algebraic geometric coding theory. And since this is a seminar of applications of algebraic geometry, so it's a perfect topic. And I look forward to your talk, Gretchen. Huh?
Thank you so much, and thanks for inviting me to speak today. I'm going to share some recent work done with my colleague Hiram Lopez, who is here, I think, as well. And I'll be talking about a new topic that we've been looking into called multivariate Gapa codes. So, of course, I'll share many details throughout the talk, but the main idea, if you would like to capture that at this moment, is that these multivariate Gapa codes and multivariate polynomials allow us to provide a generalization of the classical Gapa codes. So as we will discuss, the classical Gapa codes are used in the McEliece cryptosystem, and which is one of the candidates for post-quantum cryptography that NIST is currently considering. And these codes that we'll consider, these multivariate Gapa codes, it turns out have utility in other applications as well. So we'll see how we can use these multivariate Gapa codes to make LCD codes, which are linearly complementary dual codes, which guard against side channel attacks as well as fault injection attacks at the same time. They can also be used to create quantum error correcting codes and lots of families of long codes that have interesting properties that could be useful in varying applications. So that's the big idea. We're just going to focus on this new family of codes, and I'll tell you a little bit about their development and what we can do with them. So, of course, recognizing that not everyone here spends all their time thinking about coding theory, we'll start with some basics just to make sure that we're all on the same page, and then we'll start to see how these this generalization from using univariate polynomials to define codes to looking at the multivariate case gives us some flexibility that we didn't realize previously. All right, so the basic coding theory. So throughout this talk, F will be a finite field. And if we say an NKD code, we mean a k-dimensional subspace of F to the n. So just a subspace of dimension k of vectors of length n, where the entries are coming from the field F. And we are often interested in the minimum distance of these codes, and that's, we use the Hamming metric here as our measure of distance. So that is the minimum number of coordinates in which two distinct code words differ. And I should say that the elements of a code are called code words. So a standard result in classical coding theory is if we have a code of minimum distance d, meaning the nearest two code words differ in d positions, then that code is capable of correcting the floor of any d-1/2 errors and also recovering any d-1 erasures. And so we can see in the diagram here, that's because our code words are separated in space in such a way that allows for this. Another standard object that we use when we consider codes is the dual of a code. So again, throughout the talk, we'll just be using the Hamming metric. And so the dual of an NKD code will be denoted C-perp. And that's just the set of code words over the same field. So here we're taking C to be a code whose alphabet is the finite field with Q elements, F sub Q. And the dual then is the set of code words over that same alphabet, set of words over that same alphabet whose dot product is 0 for all code words in the original code. And so this gives us another linear code, and of course the dimension is n minus k, but the code length doesn't change. We can't usually say too much about the minimum distance, but we will be using duals of our codes as we move ahead. Another tool that's going to be important for us is a generator matrix of a code. And so because the codes that we look at are all vector spaces, they're all linear codes, that means that they have bases. And so if we take any basis for a code and take a matrix, form a matrix using the rows to put those basis elements in, then we get a generator matrix. So a generator matrix is just a way of keeping track of the basis of a code word. We typically take a generator matrix for an NKD code to be having k rows. Of course, you could allow additional rows and just be concerned if your matrix spans the code or not. But for us, we'll require we'll typically use a basis for the rows. The other matrices that will play a role are parity check matrices. And those are matrices that have the code as their null spaces. So in other words, a parity check matrix for a code C is any matrix H that happens to have C as its null space. So of course, there are many choices for generator matrix, many choices for parity check matrix for a particular code. And so when we talk about the multivariate Gapa codes, we'll be considering both generator matrices and parity check matrices, because one of the things that we wish to do is to provide different descriptions of these new multivariate Gapa codes that give insight into their usefulness as well as their parameters, very similar to how we see for the traditional classical Gapa codes. So all of the codes we'll talk about today will be defined using polynomials. And by far the most famous instance of this is the family of Reed-Solomon codes. And so we'll be building on this family. So I know, some of this is just textbook knowledge, but just to make sure we have all of our terminology and notation straight. So to define a Reed-Solomon code, we take a field, a finite field here with q elements. We enumerate the elements, we'll call those alpha sub i's. And then we can define a Reed-Solomon code for any k and n, where k is at most n and n is at most q. N tells us the length of the code. So we're going to choose some of these alpha sub i's, say n of them. Each one of those will determine a coordinate. And then k can be no more than n. And we'll get the actual coordinates of the code word by taking polynomials in the variable x with coefficients from fq of degree at most k minus 1. And so in doing so, we obtain the Reed-Solomon codes, which are the, again, most famous family, most well understood and utilized family of algebraic geometry codes or evaluation codes that we have. Reed-Solomon codes are nice and easy to understand. We can see that the dimension of the code is k, and we also know the exact minimum distance, which is rare for these error correcting codes. If we also know that n, the code length, is equal to the size of the alphabet, then the dual of the Reed-Solomon code is another Reed-Solomon code. And so that property is typically very convenient, right? The dual of the code is of the same form. However, if we allow n to be less than q, so we have a shorter code than our alphabet would support, then it turns out that the dual of the code is slightly more complicated than just being a Reed-Solomon code. It turns out to be a generalized Reed-Solomon code. A generalized Reed-Solomon code, though, looks just like the Reed-Solomon code that we saw above. You'll notice the only difference is that we have these coefficients, these v sub i's. So we can prescribe some vector v, and then a generalized Reed-Solomon code just means that you sort of weight the coordinates by the entries of the vector v. And with this generalized Reed-Solomon code, we note that the dual of any Reed-Solomon code is a generalized Reed-Solomon code, and we can say specifically what the weighting of each of these coefficients should be. So you can see that here. You can also check that if n happened to be equal to q, then all the v sub i's would be 1, and we would recover the expression above. So,
Can I ask a textbook question
yes.
for this textbook slide? So, and if I have a generalized, yes, I don't do coding theory, so I don't know. So, but if I have a generalized Reed-Solomon code and take the dual of that, is that still also a generalized one? And
it is, and I am so glad you asked, because I felt like there was something I was forgetting to say on this very slide, and that's exactly it. So yeah, if you take the dual of a generalized Reed-Solomon code, you happen to get another generalized Reed-Solomon code as well. Thank you.
nice, great.
So we will be looking at these generalized Reed-Solomon codes, and we want to kind of hone in on a particular family of those. And we define them using a particular polynomial. So later on in the talk, we're going to be working over a finite field, fq to the t. So I want to visualize, I have this larger field fq to the t, and it's going to be considered as an extension of a field fq. So now I'm going to be thinking over fq to the t. I'm going to take a univariate polynomial there, g, and then I'm going to specify some evaluation points within my field. So fq to the t is now the alphabet. And we're just going to use this g and these elements to create what looks a lot like a generalized Reed-Solomon code. In fact, it is a generalized Reed-Solomon code. We take polynomials of degree at most k over this field fq to the t. We evaluate those at the evaluation point, these s sub i's, and these coefficients here, now instead of being from that vector v, they're specified by this polynomial g. And of course, in order to do this, because we're taking the inverses of g evaluated, the s sub i's will require that g be non-zero at each of those elements. And so this is a particular type of generalized Reed-Solomon code. Not sure why it's taking some time to advance. Let me go back. Okay, there we go. So in the particular case where we fix g and we take k, remember determines the maximum degree of the polynomial that you can evaluate to generate a code word. In fact, these f sub i's have to be degree at most k minus 1. If instead of allowing both g and k to vary, we fix the polynomial g, and then we say we're going to take k to be the degree of g, then we get what's called a generalized Reed-Solomon code via a Gapa code. And so when we say that, we just mean it's a generalized Reed-Solomon code of this form, where k is the degree of g. So that means that the polynomials f that we evaluate to get code words are of degree at most the degree of g minus 1. So these generalized Reed-Solomon codes, I guess they've been around forever, if you think about it, since the beginning. Forever, it goes back to the beginning of generalized Reed-Solomon codes, by the way. But it's a special case. But they were first really, I think, studied just last year in a paper in 2001, where they identified this particular family of generalized Reed-Solomon codes because they could do some interesting things with it, like determine which of these codes are linearly complementary dual and some other nice properties. And so we'll be using this construction, these generalized Reed-Solomon codes via Gapa in the multivariate Gapa construction. I'm sorry, I'm having some trouble advancing my slides bit here, where we should be. So of course, these are all the codes that we've been talking about depend on, up to this point, depend on polynomials in a single variable. We also have multivariate polynomial codes like the Reed-Muller codes that you see defined here, taking your evaluation points now to be an m-dimensional space over a finite field, taking the polynomials to be of tilde degree at most k, we get a Reed-Muller code. So generalization of the Reed-Solomon idea. And of course, we can write the parameters down for these Reed-Muller codes. I mentioned the Reed-Muller codes because we're going to be talking about multivariate polynomial codes, and I don't want to suggest at all that the multivariate Gapa codes are the first of those by any stretch of the imagination. Certainly, we have our Reed-Muller codes. We also can be more flexible in allowing ourselves to choose different evaluation points, as well as different polynomials to define the code. So we have a lot of flexibility that's sort of hinted at in the Reed-Muller construction. because we could change this family of evaluation points. Like maybe we don't have to take all of them. Maybe we just take select points from this m-dimensional space. Also, maybe we don't take just the polynomials of bounded degree at most k-1 in m variables. Maybe we do something else. And so there are more general evaluation codes, such as a monomial Cartesian code. So here, I'm not going into all the technical like details and results, but I just want to give the idea that, you know, we could take a subset of polynomials instead, and we could also take some subset of evaluation points and produce an evaluation code and study those and get interesting results in that way. And so we will be looking at, we'll be using some Cartesian codes later on. So this is something that will come back. All right, so what do we do though with these codes? So when we started thinking about the multivariate Gapa codes, which we'll define in just a moment, we were thinking about the McEliece cryptosystem, and which you may be familiar with already, certainly. And so, but just for purposes of discussion, let's think about what that looks like and what the ingredients are. So here, rather than looking at the classic McEliece, which uses as a code the classical Goppa code, I want to think about just abstracting, like using the McEliece idea with any code, okay, which is a bad idea, by the way. Don't ever actually do that, but that's what we're looking at on this slide. So I want to take C to be a linear code of length n, dimension k. I want the minimum distance to be at least 2t-1, and that way the code is capable of correcting at least t errors. We want to identify a particular generator matrix G, which we'll use. It's also important that the code have an efficient decoding algorithm for reasons that we'll see in just a moment. So in the McEliece cryptosystem, we want to take this very structured code C and specified in this particular way via generator matrix G, but we want to sort of disguise that structure through multiplication by a couple of other matrices. So S and P are permutation matrices. I'm sorry, S and P are random matrices. S is invertible, P is as well. P is a permutation matrix. And rather than publicize what G is, instead we disguise G by multiplying on either side by these two matrices that we've just chosen. So the public key, so this is all kind of the background setup. The public key for the cryptosystem is this product and T, which you could think of as the error correcting capability of the code. And then the private key consists of the parts that you see here, the matrices S and P, as well as this efficient decoding algorithm D. The way encryption works is if you have a message M, which you wish to send, in such a way that if it's intercepted, it can't be, just decrypted without too much work. What would you take, or read without too much work? So what would you do? You would take M, this message of length K, you would multiply it by the public key matrix GPub, and you would add an error vector of weight at most T. T, remember, is the error correcting capability of the code. So if you're thinking about an Alice and Bob situation, Alice does this and sends it to Bob. And then Bob, being the intended recipient, let's see. So here we have the message M, that is the encrypted message, and then what would happen is, having access to this private key, you can multiply on the side by P inverse, right? P, remember, is that permutation matrix. When you do this, of course, it's allowing you to cancel out part of the GPub matrix. Notice also, though, that we have this error vector here. Because P is a permutation matrix, we're ensured that the weight of this product here is at most T. And so we end up with what? The original message M times this S times G, which, remember, we don't know, and Eve would not know S or G. And then this error vector here, which is now permuted. But with access to the private key, the decoding algorithm can be applied to this vector here to get rid of the errors. And so what we end up with is m times s. And of course, the private key includes s. And so then that way you can get back to the original message m. So of course, if we think about how this is done, it's important that the original code not be revealed to potential attackers, because if they have access to that, then they have access to the decoding algorithm, and of course, then there's no security. And so the idea is to have a code that's used in this cryptosystem that is somehow user-friendly enough that it can be represented compactly, perhaps even more compactly than just a generator matrix alone would suggest. But it when you apply the matrices S and P via that multiplication, when you take that product, G does not have enough structure to retain it via this product. And so that's kind of the danger in applying code-based crypto with codes that aren't the classic Gapa codes, is that they tend to have, if you start with a structured code, such as a Reed-Solomon code, then that structure seems to retain itself even via this product. And so the public matrix reveals more information than it seems like it should. And so that's problematic. And so sort of one of the nice things about Gapa codes is that the Gapa codes, they start off being defined over a large field, but then through this notion of a subfield subcode, they're actually live over a base field instead. And somehow this kind of fiddles with the structure and seems to make it less obvious, so that the initial structure of the is not retained when you go from G to GPub. All right, so what that means is we need to look at, for a code, what is the subfield subcode construction? Because we're going to use that with our multivariate Gapa codes, which I promised to define shortly. So here, as I said earlier, we're going to work over this large field. So we're going to start up here. We're going to have some of our elements up top. In particular, if I had a code over the large field, the extension, then it would make sense to consider only, if I wished, those code words that lived over the ground field. And that's the subfield subcode. So I start with a code up here, and then I'm going to take the collection of code words that live in the intersection of the code and the vectors over the ground field. And of course, when we do that, we get a code of the same length. We can say something about the dimension and a little bit about the minimum distance as well. And so we get a code over the ground field. Another way that we can get a code over a base field would be to just take the code words, and for each coordinate of the code word, just take its trace, right? So we have the trace map here at the top, a map from the extension field down to the base field. And so that's the way we define the trace code, is for every code word, I'm just going to take the trace of each of the coordinates to get a new code word. And of course, this code word is going to be something that lives over FQ. And so, of course, I'm sure we're all thinking the same thing at this point. So I have two different ways at this point of getting from a code over a big field to a code over the small field, and are they related? And before I say that, I should say something about the trace code itself. The trace code itself, of course, has the same length. We can say something about its dimension. Its dimension is bounded between k and t times k, where t is the degree of that field extension. We get a bound on the minimum distance. And here's what we were all wondering, the relationship between the trace code and the subfield subcode. So Delsart's theorem says that if I start with a code C and imagine it's over a large field, say with q to the t elements, if I take the dual of that code and then take its trace, that's the same as if we took the subfield subcode of the original code and then took its dual. Another way of saying this, of course, is that the subfield subcode of the code C is the dual of the trace of the dual of C. All right, so with all of that behind us in our crash course in coding theory, or review, we're ready to define the multivariate Gapa codes. And we'll be using all of these ingredients that we've just talked about. All right, so to define a multivariate Gapa code, we're going to take a product of polynomials and m variables. So, so now we're looking over fq to the t. So the polynomial g is going to have coefficients in a large field, perhaps, and it's going to be an m-variate polynomial, but each of these factors, these g sub i's, they're univariate in a single polynomial, in a single variable x sub I. Then we're also going to define our evaluation points. Our evaluation points are going to be in the m-dimensional space over this large field, q to the t. Just for technical reasons, we'll be sure that none of them are the empty set. And we want to enumerate the elements of this Cartesian product. We're going to enumerate the elements, say S1 through Sn, because we'll have a coordinate of a code word associated with each one of these. These are our evaluation points. All right. So we also want to assume that these points, these S sub i's, are chosen so that G isn't 0 on any of them. And then finally, we have the multivariate Gapa code, which is the collection of vectors over FQ. Remember, G came from FQ to the T, that's where its coefficients live. But we're going to take just those vectors in FQ that satisfy this condition that you see here, mod G. So you can see the C sub I showing up on top. So you can think about this as kind of a weighted sum according to the coordinates of the code words. And so you might think like this is maybe kind of a not so nice definition. I don't know what you think. Maybe it's nice, maybe it's not so nice. And in trying to make it nicer, I'm not sure that this really helps, but if you really want to see it as a weighted sum, maybe it looks a little bit better in this way. But here we see the S sub i's showing up. Remember, the S sub i's were the evaluation points. And so here our evaluation points are in m-dimensional space. And so the S sub ij's are the coordinates of those points. We see G showing up. G was that initial polynomial that we started with that has that factors into a product of univariate polynomials. And those are the important components. So we can see the classical Gapa codes as a special case of these by taking m equal to 1. Remember, m is the number of variables that we use to define the polynomial G. So if we take G to just be a univariate polynomial, then we get a much nicer expression for the Gapa code, and this is the classical Gapa code. So the multivariate Gapa codes do have as a special case the classical Gapa codes if we just look at that definition when we take only a single variable or m equal to 1. Of course, there in that case, like we said before, G is a univariate polynomial. We can also notice that the S sub i's, these evaluation points, where do they live? They live in one-dimensional space. They just live in the field FQ to the T. But remember, ultimately, we take only those words that have coordinates in FQ.
Why is the denominator non-zero?
What's that?
The denominator x minus si, why is that non-zero?
Yeah, so thank you. So I tried to write things compactly on the slides, and so there might not be the correct hypotheses, full hypotheses given for every result that we mentioned. Yeah, sorry. Yeah, so I probably should say something early on about the condition on the S sub i's. Thank you. Yeah. Yeah, I didn't think about that. Yeah, because there's actually a lot of hypotheses, and so you might not see all of them, but they're in the paper. So if you have questions after looking at that, be happy to talk with you about that. Another special case that we can get is, so this is taking just m equals 1. When m is equal to 1, we still have the field extension where we're working over FQ to the T, and then we restrict to FQ, or we only take the words over FQ. If we also set not just m equal to 1, but also t equal to 1, so that we have a trivial extension, then we get actually that these multivariate Gapa codes are just the generalized Reed-Solomon codes via Gapa that we saw earlier. And so it's kind of a nice analog. So if we take a look at these multivariate Gapa codes, then as coding theorists, the first things that we want to know typically are, what are their parameters, length, dimension, and minimum distance. And so we can see, and also what are they good for? Why are they worth talking about? So we can see that the length of the code comes from the cardinality of the set of evaluation points. We chose our evaluation points, remember, in m-dimensional space over the large field, which means that these codes can have length up to q to the t times m, which I don't know if that's good or bad. It depends on what you're comparing it with. But if you're thinking about the standard codes that we might compare these to, you might think about the classical Gapa codes or generalized Reed-Solomon codes or Reed-Solomon codes. And in those cases, if we were to take, say, m equal to 1 to get the classical Gapa codes, then the length of the code we could define as at most q to the t, which is the size of the alphabet. And so they don't compare. So these actually compare very favorably in terms of length. We have much more flexibility to build long codes if we wish than we do with the classical Gapa codes or the generalized Reed-Solomon codes. We also have the flexibility of choosing t to be larger, so that if you were comparing it with a Reed-Solomon code where your alphabet would have to be of size q to the t to the m, you'd have a much bigger alphabet needed to define the same code. All right, so in order to say more about the other parameters, we'll need to investigate the codes a little more carefully. It turns out that these multivariate Gapa codes are related to some other families of codes in the literature in ways that we did not realize when we started this project. So it's kind of surprising in some ways when you see it, at least it was for us the first time. But it turns out that they're related to something called, well, tensor products of generalized Reed-Solomon codes. Basically, if we take those generalized Reed-Solomon codes that we saw before, the ones that depend on a polynomial. So remember the multivariate Gapa code is defined using a polynomial g that factors as shown here. So each one of these factors I could use to define a generalized Reed-Solomon code, and I could take as the evaluation points the appropriate factor here in this Cartesian product. If we did that, then we took the tensor product of all of these codes, we get another code called a tensor product of those codes. You can say something about the parameters of these codes, certainly length, dimension, and minimum distance. Notice that the dimension and minimum distance both depend on the degree of the polynomial g, as well as the degree of the factors, as well as the size. These n sub j's, those are the sizes of these s sub j's. I might not have said that in the slides. What's nice about these tensor products is that we can write down generator matrices for them because they're just tensor products of generalized Reed-Solomon codes. And so that means that we have an explicit expression for these tensor products. So a generator matrix is basically found by taking the evaluation points and evaluating them at polynomials in degree up to a, where a runs through all of the vectors in this set. And then we weight them by the inverse of this defining polynomial g evaluated at each of the evaluation points. It's kind of a handful or a mouthful, but the main thing is just that you can explicitly write down what this generator matrix is. That's going to be important for us as we go to try to understand the multivariate Gapa codes. Because it turns out that the multivariate Gapa codes have as a parity check matrix the matrix we just saw. So in other words, if I take a generator matrix of that tensor product of generalized Reed-Solomon codes that, remember, depend on G, then the multivariate Gapa code that we define using G is actually the, well, you might want to say it's the, it looks like the dual of T, but remember T is a generator matrix that lives over FQ to the T, small t. And so this is the set of code words over FQ that satisfy this parity check equation. So that means that the generator matrix for the tensor product of generalized Reed-Solomon codes that we saw earlier via Gapa turns out to be a parity check matrix for the multivariate Gapa codes. Parity check matrices arise in decoding algorithms, and so we're really happy to have our hands on those. So that means at this point we know a few things about the multivariate Gapa codes. We know their links, and we know something about their generator matrices, but we still don't have a handle on the other parameters. And so in order to understand more about them, we turns out that we can use a relationship between the multivariate Gapa codes and another family of evaluation codes. This project felt like surprise after surprise, because these codes that that are in the literature or that we've studied before for other purposes keep kind of popping up in surprising ways. So let me share one of those surprises with you now. So, and that's in terms of these augmented Cartesian codes. I'm sorry to have like so many families of codes going on here, but they're closely related, but they each are slightly different and offer something new that we need. So here to define an augmented Cartesian code, we'll take, again, a Cartesian product of sets that are subsets of FQ to the T. So we have our evaluation points living in that m-dimensional space over FQ to the T. We need some polynomials here. We can think about this as the vanishing polynomial. If I take just one variable and fix J, then I can think about this polynomial L sub J. And then I don't need L sub J directly. I actually need the product of its derivatives. And we use this polynomial L to define another evaluation code. And so remember the monomial Cartesian codes we saw before? All we really have to remember is that we're taking polynomials, evaluating them at points to generate code words. And sometimes we have coefficients in front of them. Well, these augmented Cartesian codes, they come about in exactly that way. We take a polynomial f that has, well, it's based on the monomials in the set that you see here. Those are the polynomials that we evaluate. And then we weight them by these coefficients. And these coefficients depend on this polynomial L, as well as a specified polynomial H. And so the details maybe aren't so important for us, but I did want to share a little bit about where these codes came from, because I think it's, again, surprising. So Cartesian codes have been studied in the literature. And in another project, we were looking at linear exact repair for Cartesian codes and their relatives. And it turns out that the results that one might get typically involve low rate codes. So you can do this thing called linear exact repair for low rate codes like Reed-Muller codes. However, it turns out that you can augment them and by augmenting, we mean increasing the dimension by taking more polynomials than what one would typically take. So I think I have some pictures to show you. Yes, okay. So in this picture here, we'll start off here. So what you're looking at here is the set of exponents of vectors that we would evaluate, the set of exponents of polynomials that we would evaluate to get code words of a Reed-Muller code. This is a Reed-Muller code over the field with 7 elements. That's what the 7 here is, that's the Q value. And so we would evaluate at 7, at the point over F7 squared, because here this 2 indicates that our M is 2. We're taking 2 degree bivariate polynomials here. And 4 is the upper bound on the degree. So if we were taking a standard Reed-Muller code, we would evaluate all of the, x1 to the A, x2 to the B, where AB is a point in this diagram. And so we take this sort of triangle down here. We noticed when we were looking at linear exact repair, which was known for Reed-Muller codes, but Reed-Muller codes have this low rate or lower dimension than what we were interested in, we realized that we could augment the codes by including more points, more polynomials, which means we're increasing the number of code words, we're increasing the rate of the code, and still do this linear exact repair. That's a separate project. But what happens is you can actually do the same things that you did before, that you wanted to do before. You have a higher rate, and you have still this this opportunity to repair erasures, which is not the topic that we're talking about today, but this idea of augmenting is. And so this is an example of an augmented Cartesian code. So if I were looking at a traditional monomial Cartesian code, I would have this triangle down here, but now I can augment it and actually increase the rate. Okay. So we're not doing that. We're not considering augmented codes here to increase the rate. It just turns out that the augmented codes are the ones that show up when we go to study multivariate Gapa codes. So the results using these different families of codes include the fact that the dual of a multivariate Gapa code is the trace of one of those tensor products of generalized Reed-Solomon codes. And then that gives us information about the other parameters, the dimension and the minimum distance. And so for one of these multivariate Gapa codes, we actually, using the trace construction that we saw before, as well as a relationship with these augmented Cartesian codes, we can see that the dimension of a multivariate Gapa code is between these two values. So this T here is the degree of the field extension. So that gives us a bound on a lower bound on the dimension. And we also get a lower bound on the minimum distance of the code coming from the degree of G, or the degree of the components of, or factors of G. Other things that we can do with these codes, we can determine their hulls. And so the hull of a code is the intersection of the code and its dual. I feel like we don't talk a lot about hulls, but in some ways we've been talking about them for a long time because we've cared for a long time about whether codes are self-orthogonal or self-dual. And those are both properties that can be described by the hull of a code. And certainly the notion of whether or not a code is linearly complementary dual can also be described by the hull. The hull is just trivial. Hulls also come up in several algorithms related to code-based cryptography, such as the splitting algorithm, and also coming up in this permutation code equivalence problem as well. And so if we know the dimension of the hull of a code, then that tells us something about the complexity of various algorithms that might be of interest. So we can say something about the hulls of some codes with a little bit of additional work. This result is kind of a technical one, but I have to share it because we're familiar now with the idea that we have this multivariate polynomial G that we've used to define this multivariate Gapa code, but now it has a partner. Well, or at least sometimes it does. So if you see a G like this, and you can find an F that satisfies these conditions, then it turns out that the dual of one of these tensor product of generalized Reed-Solomon codes via Gapa is another one of the same form. That result reminds us of what we talked about for Reed-Solomon codes earlier, as well as generalized Reed-Solomon codes, the idea that the dual is one of the same form. But I'm really sharing this with you because I need you to know that sometimes when we have a polynomial G that defines a multivariate Gapa code, it has a partner F. This partner F is important when describing the hull. So if I were to take the hull of, say, one of these tensor product codes, then it turns out to be another tensor product code, but the defining polynomial, instead of just being G, the original one, it's the GCD of G and F. And that turns out to be the hull also of one of these augmented Cartesian codes. Also, F and G go hand in hand in saying something about the hull of a multivariate Gapa code, because if these conditions are satisfied, then the hull of one of these multivariate Gapa codes contains a multivariate Gapa code whose defining polynomials of least common multiple of this F and G. And they're the same if the extension is trivial. We have other results about characterizing or determining when situations when these multivariate Goppa codes are LCD, self-orthogonal, self-dual, all this good stuff. I have several examples, but I don't really want to go into the details, but just to say that we can use these multivariate Goppa codes to come up with infinite families of long codes, which are LCD, over small alphabets. So these LCD codes are the ones that protect against side channel attacks and fault injection attacks simultaneously. And so we can see over this fairly small field, we can construct, very long codes of reasonable dimension using this multivariate Goppa code construction. Using, slightly different sets here. So to get the evaluation points, slightly different polynomials, we can also get large families of self-orthogonal codes over this, over a field like this one. And these are just kind of representative examples. And the same thing for self-dual codes. I didn't have time to share with you the results on the quantum error correcting codes, but we can get families of those as well. There's still lots to be done with multivariate Goppa codes. You'll notice that I didn't talk so much about or at all about decoding, but efficient decoding algorithms are important in this work, and that's something that we're currently working on. We have some decoding algorithms, but the more efficient, the better. So that's all I have to share. Thank you.
Gretchen, many thanks for this very clear talk and interesting. Yeah. Other questions? So either in the chat or we can also promote you if you directly want to talk to Gretchen. There are not so many people in the audience, so we could move them over. Anybody who wants, make a sign. And I might ask, you have also a subfield subspace construction here for the multivariate case, because you mentioned McEliece, and this is absolutely needed there. If you do it Reed-Solomon-like, not with a subfield construction, do you have some generalization of the Schur product, which is kind of the distinguisher to attack, Reed-Solomon type codes?
Yeah, so I expect that something like that is true here. So in fact, I feel certain enough that I haven't worked out the details of it. It's so funny that you asked about that, because I thought about that just this morning, that I haven't fleshed out the details, but I feel pretty certain that you will see exactly the same thing as in some of these other, like Reed-Solomon cases, the cases of many of our algebraic geometry codes, where you take the Schur product and the dimension drops dramatically because you have a code of the same form. But there's some details to work out there that I.
Multivariate version of Schur product.
What's that?
You have a multivariate version of Schur product.
Yeah, so I think it would be a little bit, there's a little bit more to keep track of. And like I said, I haven't actually checked everything, but I just sort of was thinking about that it almost has to be the same way. That's not a very clear answer, I'm sorry. Yeah. I'm very confident though that it suffers the same thing that we see for our Reed-Solomon codes, right? You take a product of two of these codes, you get another code that either is of the same form or it's contained in one, which is also not good. Yeah. Great question though.
Yeah, so there is actually, I think, Tanya or who had a question. Yeah, here's Tanya.
Yeah.
Sorry, this is complicated because I was not promoted. I was kicked out, so I didn't hear the end of your answer. So at the beginning you were noting it with cryptography, and now you're saying, well, maybe it can be attacked. Some cases there are with the normal binary Goppa codes, we lose enough structure, and also here it might be because you have the subfield construction. that you don't get the structure loss. So the
Yes.
show square product I see as an attack tool when I think of it as a code-based crypto application. And so I wonder how far you would get.
Yeah, so actually the question I think was about if you don't do the subfield subcode construction.
Oh yeah, okay. If you do it with field, then yes, I agree.
Yeah, and again, I haven't worked out the details, but I think it should work like that just the same. I mean, one can imagine this. But if you do take if you actually do the construction where you are taking the subfield subcode, then I would think that, those rules don't apply, but I mean, it's always possible, of course, that there's other ways of revealing structure. I think, one of the, you were asking about the motivation coming from code-based cryptography. I think,
well, I mean, you're presenting code-based crypto, so I figured you were thinking of these for that application.
Yeah,
so I see more applications at the end of your last slide where you have the literature.
Yes, and certainly that's still on the agenda of what we would like to better understand is there utility from these codes here that would allow us to work over allow us more flexibility in terms of the choice of codes for McEliece, but there's still quite a few questions